Okay, we talked about how to set up models and how to run, how to estimate the coefficients. Now let's spend a few seconds talking about how to measure the model fit and the validation. So we talked about the basic checks. Whenever you run a regression model, look at the R-squared values. This tells you an overall goodness of fit. And the individual coefficients, you do the t-test, find the p-value, see if they're statistically valid. Now there's many other tests you can use. In fact, you can use the F statistic that LINEST gives you to also see a measure of goodness of fit. It's a little bit different, but you can also use that. But you should also look at some basic assumptions that the regression model uses and check that they're still valid. So one of those is the normality of residuals. Remember, one of our base assumptions is that my error terms were distributed normally with a mean of 0 and some standard deviation. So therefore, I would expect that a histogram would show me something that would be kind of normal. Now, it is kind of centered around 0, right? But it doesn't look so normal. This is the distribution of the residuals from model number 1. And so I would go back and say, you know what, I'm not doing so well here for my normality assumption. I wouldn't probably use this model. And in fact, I would check, because it looks like I'm kind of over biased down here. I'm pretty heavy on the negative residuals. But that's one of the first checks you should do. Always look at your residuals, see if they're normally distributed. You can do a formal test with a chi-square test or a Kolmogorov-Smirnov test, and more sophisticated packages will do that for you. But you should also look at something called heteroscedasticity. It's a complicated word, but all that it means is as my variables, the range of my variables, does my standard deviation of the error term differ? And so what I have here in this chart is the temperature. This is model 1's residuals, and the temperature goes from 35 to 95, and on the vertical axis is the residuals for each of those observations. So the question is, if we had homeoscedasticity, then the standard deviation would be pretty constant along the entire range of the temperature. But as I look here, it doesn't look so constant. It kind of looks like we have a little bit of a downward trend. Now, there's not much data here. I only have 24 observations. But it looks like it's not doing so well with heteroscedasticity. In fact, it's looking like the residuals do change over time. And they get the higher temperature, the standard deviation is different from the lower temperature. The third assumption you want to check for is autocorrelation. And this is very common when I'm doing forecasting for time periods or time series. And is there a pattern over time? So again, it's just a scatter plot, and instead of temperature, it's just for the time periods. And so we want to make sure that the residuals are independent. So if I look here, it looks pretty independent. There doesn't seem to be any pattern. Now, for example, if I had a pattern that looked like all the residuals over time did something like this, right, where it started low and then went up and down, then I'd say, oh, something's going on. There's autocorrelation going on. But in the data we have, it doesn't look so bad. It doesn't look so bad for autocorrelation. You also want to look at multicollinearity, and what this means is that if some of the independent variables are not really independent, they're correlated. So look at a correlation matrix, see if each of my independent variables, is there any kind of correlation, and there will be some usually. But then the big one you have to check is the use of dummy variables. So I didn't talk about it too much, but when we looked at whether school was in session or not, we had one variable, and I think I called it x3, and we said it was equal to 1 if I was in session, and it's equal to 0 otherwise. Now you might ask yourself, why didn't I create two variables? One for x3 when school's in session, but why not another one, and we call it x4, that's equal to 1 when school is not in session, and equal to 0 when it is in session? Well, the reason why I don't is because that would over-specify the model. Because once I know the value of x3, school's in session, x3 equals 1, then I know the value of x4. It would be 0, because these two variables would be totally correlated, 100%. It would be correlation of 1. So the idea here is whenever I use dummy variables, and in this case for a school being in session or not, there's two states, right? It's either in or it's out. Therefore, I only want n minus 1 variables to capture that. Two states, n is 2, I only need one variable. Let's say I have a flag for each of the seasons, 4 seasons. There are 4 seasons, n is 4. How many flags would I need the most to capture that? 3. 4 minus 1. So you have to be very careful when you use dummy variables that you do not overspecify, because what will happen is the model just won't run. It'll give you an error. So that's an example of multicollinearity. So we went over these in really quickly, but if you're going to do this in depth, you really should dive in a little more, and you'll probably use a more sophisticated piece of software. And every piece of software worth its salt will use and check for all of these different things, whether it's R, SPSS, SAS, Minitab, anything else. Even Excel has built-in regression tools, and they're more sophisticated. But at the heart of it, they return the same data that our LINEST function does. Okay, so that's about model validation. Let's just talk a little bit about fit. And so let me give you an example. This is 4 data points. And so this is for time period 1, 2, 3, and 4, and the sales during that time period. And this could be in, I don't know, thousands of dollars of sales, and time is days, whatever. And so the question is, which model is better fit? So here's a linear model. You can see I did a quick regression just with those 4 points, and I come up with this equation that y, sales, is equal to 0.4 times x, that's the time period, plus 4.5, and had a very low r squared, 0.16. But I could improve upon this and enter a quadratic equation. Again, it's just linear in the equations, in the parameters, so it's fine. And I get a 0.5x squared minus 2.1x plus 7, and I get a slightly better r squared. So my goodness of fit goes up. And then I have this one, and this is using a cubic model. And so you can see that the estimation of the term that minimize this, and look at my r squared, it's 1. How awesome is that? So the question is, which of these is better? Which is the best fit? Which one I should use? And unfortunately, a lot of times students or first-time forecasters will naturally gravitate to this one and say, well, this is a better r squared. You know, better r squared is always better. But remember, we're trying to come up with a forecast, and we're coming up with a forecast for planning purposes. So let's look at what the estimate of each of these models would be for time period 5, right? So for here, for the linear model, the estimate for time period 5 would be about a 6.5, so right in there. For the quadratic equation, it would be 9, so let's see, where's that? Like up here. For this cube, even though it had an r squared of 1, really good fit, the estimate for time period 5 would be 23, so that's like up here, right? So that would be the next estimate. So you got to ask yourself, just because I have goodness of fit to history doesn't mean it's going to be a good fit going forward. So you have to avoid overfitting. It's easy, it's tempting to maximize that r squared, but you've got to use some judgment of the underlying behavior you're trying to model.